Hello YouTube. In my last video we started our journey with solving trig equations, very basic trig equations, and how you do that using unit circle and inverse trig functions. In this video we're going to talk about equations that involve a few more steps before we can use inverse trig functions, but really are the same thing that we just did in the last video. And we're going to build on how you present your answers in general. Okay, so let's go ahead and take a look at these. I've got 4 examples here. It says solve the following equation for the angle x. So x is our angle. We're looking for an angle that when I plug it into this equation would give us a true statement. All right, so we want to express our answer both in degrees and radians, and we want to check our solutions. Oh, and by the way, this is very important. It means that our angles are only between 0 and 360 degrees. We don't have to give any angles bigger than 360 degrees. So let's go ahead and start with what we know about trig equations, at least from the last video, is this. You have to isolate the trig function. You have to get this thing by itself. So we're going to treat this just like an algebraic equation. If I had 2x minus 1 equals 0, I would add 1 to both sides and divide by 2, which is the same thing we're going to do here. So let's go ahead and show our work. We say plus 1 plus 1. We get this right here. We say, well, then 2 sine of that angle is going to be equal to 1. And now we're going to divide everything by 2. So if I divide this by 2, and we'll leave it as a fraction. We don't want decimals. We want fractions. So we say sine x is equal to a half. Okay. So now that we've gotten the trig function by itself, here's the part where we're saying, okay, what we'll do is we'll take the sine inverse to undo this, but we have to do it to both sides. Oh, and by the way, that sine inverse cannot go in the back of this. That is wrong. Okay. It is a function. It is a function of x. We cannot say, hey, like I'll just put the f over here and make it mean the same thing, okay? But that being said, what we know about inverse functions is that they undo each other, and now I'm left with just x, and I know that x equals this. As a matter of fact, if you can get this on your paper, I'd have to give you some credit because you have the right answer right now. It's just that we have to answer the question, which is what angles between 0 and 360 actually produce this? Okay. So here's where we're going to do it a little bit differently in this video. We did in the last video this. Let me pull out my unit circle here. In the last video we said, hey, what angles give me a sine value of positive a half, which is what this is right here. So what angles give me a sine value of positive a half? And what I want to show you is this. In terms of positive a half, where would that occur? We'd say, look at the y values around the outside of this. I get a positive a half at 30 degrees, and I get a positive a half at 150 degrees. What I want to do in this video is basically recognize this. The reference angle, so that would be x party hat, has to be some sort of 30-degree reference angle because I know that I can only ever get the sine of something to come out to be a half if and only if I was talking about a 30-degree reference angle. So here's what we're going to do. We are going to sketch kind of a rough xy coordinate plane, and we are going to draw in all possible 30-degree reference angles that we could conceive of. So we say here's a 30-degree reference angle. I'll even sketch this one in. We say 30 degrees. We're going to sketch in a 30-degree reference angle over here. We're going to sketch in a 30-degree reference angle down here and a 30-degree reference angle over here. And so what I want us to know is on all of these, the reference angles, that's this guy, these guys, they are all congruent. What I want to know is what angle between 0 and 360 gives us a positive a half for our sine values. So here's where we're going to figure this out. Using this fact that all students take calculus, this is the fact that all trig functions are positive up here, sine is the only thing positive here, tangent is the only thing positive here, and cosine is the only thing positive here. I'm saying I got a sine value that came out to be a positive a half. It had to happen at one of these angles because they all get a half or negative a half. So we say the two angles where my sine would be positive would have to be up in the first quadrant or the second quadrant if we're talking about sine. So I'll even switch out colors here. If we switched over to like a green and show you, then we say the two angles are here, okay, 30 degrees. That was one of them that worked. And the other one where sine is a positive half is over here. So we say, what angle is this? We have to use the fact that this is 30 degrees right here to tell you this full angle, but we'd say that is 150. So we say x equals 30 degrees and 150 degrees. And we wanted to report this in radians as well. So remember, 30 degrees, that is a sixth of pi. As a sixth of 180 degrees, and 150 degrees would be 5 30-degree angles. So we say 5 of these pi 6 things. These would be my solutions here. Okay. So one real quick thing before we go ahead and confront these. What I want you to notice is that we just got these answers in degrees and in radians. As a matter of fact, we said answers between 0 and 360, or 0 and 2 pi. We got these sets of answers here. But keep in mind, if I were to go back to this diagram you see here, I could think of another angle, as a matter of fact, that would still give me a positive a half for sine, and it'd be that angle right there. And as a matter of fact, we say that would be the angle 360 degrees plus another 30. This would be 390. And I could have gotten this 390 by really throwing another 360 on to 30 degrees here. So we say not only do 30 and 150 give us a sine value that comes out to be positive a half, but also anything coterminal to 30 degrees or 150 degrees. Whoops, 150 degrees will work. So what this means is, we're just going to get into a habit of doing this, but what this means is, since the sine is periodic and it has a period of 2 pi or 360 degrees, then we say if I were to add multiples of 2 pi or add 360 degrees on top of the original angle, I'd say, well, 30 degrees plus another 360, I'm back here again, plus another 360, I'm back here again, plus another 360, I'm back here again, plus another 3. Okay, what we're going to do is we're really going to express our angles this way, in degrees. We would say not just 30 degrees, but 30 degrees plus 360 degrees times k, where k is an integer, a whole number. And basically what this is saying is I could add on any number of rotations, full rotations, onto 150 or 30 and still land in the same spots. So to list this in radians, by the way, we would have said 30 degrees, which is pi 6. We would have said plus 2 pi k. Remember, 2 pi is one full rotation. And we say 5 pi 6, which is this 150 right here, we could say plus 2 pi k. So when do I do this? When it's asking for all possible solutions. Okay, so the difference here between our problems is, do you want answers between 0 and 360, or do you want every single stinking possible answer that could ever be, infinitely many of them? So when we look at these last 3 examples down here, where it says solve this equation, and your angle is between 0 and 360 degrees, check your solutions, also interpret your results graphically. Well, I'll tell you what, let's just go ahead and start by solving. So I have 2 sine of theta minus 3 equals 0. Okay, and so to solve this, again, we're going to have to add 3 to both sides, undo our addition here. We get 2 sine of theta is equal to 3, and then we'll divide both sides by 2. This is an interesting case that I want to bring up here, but we get sine of theta is equal to 3 over 2. So what this implies is, if we were to do the sine inverse of both sides, sine inverse, we get these to cancel. We get our angle to come out to be this. The angle is sine inverse of 3 over 2. Now, I don't know what I could take the sine of to get 3 over 2. As a matter of fact, I just want to point this out. What could I take the sine of to get, this is 1.5 as a decimal. And the thing I know about sine is this. If we were to actually graph this, and I have a graphing calculator open here, we say y equals sine of x. We know what sine of x looks like here. Let's go ahead and zoom in a little bit. We know that it has an amplitude of 1, so it goes up to 1 and down to negative 1. Let me put this in projector mode here. So up to 1 and down to negative 1. So what I'm really asking is this: where would the sine of x be equal to y equals 3 divided by 2? And you notice that 3 over 2 is this horizontal line that's right here. I'm saying, where do these two graphs ever meet? And what you can see is these two graphs will never meet. As a matter of fact, sine is always between negative 1 and 1. So if you're asking this question, what could I take the sine of to get 1.5? The question answer is never. And so I wanted to check that graphically. We did check it graphically. I also want to check it on my calculator here. So what I'm going to do is I'm going to say 1.5, head over to my sine inverse key. I'm going to hit sine inverse, and it says there's no number that exists to do this. So what you're going to write here is essentially this: theta, there are no solutions, or there are no angles for which this is true. This is true. Okay, so I'm going to bury these last two ones a little bit more quickly here. Again, to isolate the sine value here, I would subtract 3 from both sides. So I say 2 sine of x. When I subtract root 3 is going to be negative root 3, and we'll divide both sides by 2. Okay, so we get this. We get sine of x is equal to negative root 3 over 2. This is one that I actually recognize here. So we say x is sine inverse, if I do sine inverse of both sides, of negative root 3 over 2. So let's start with this. What can I take the sine of? What reference angle can I take the sine of to give me root 3 over 2 in the first place? And I recognize that I had to have some sort of 60-degree reference angle. So what we're going to do is we're going to sketch in all possible angles that have 60-degree reference angles right here, 60-degree reference angles. And I'm going to ask, okay, where would sine come out to be a negative root 3 over 2? Well, using what I know about the xy coordinate plane and my trig function values, we say all students take calculus, where would sine be negative? And I recognize that it'd have to be either in the third quadrant or the fourth quadrant. So our two angles are these, this and this. Okay, so we say, what are these angles? Well, the first one would be 180 plus another 60 degrees. So this would be 240 degrees. So it equals 240 degrees. Or right here, we say all the way around here, this is 60 degrees shy of 360, so this is 300 degrees. Sorry to go different colors here. But we could also say this is 4 of these pi third things, or 5 of these pi third things. And then the last one we're going to look at here is this reciprocal trig function example. We're still going to add 2 to this side. So we say root 2 secant of x is equal to positive 2. We're going to divide everything by root 2, which gets rid of this. And we say, all right, well then secant of x is equal to 2 over root 2. I'm not going to rationalize this yet because here's what I want to do. I know that this is the reciprocal of cosine. Now, I do want to say this. There is no secant inverse, but I do know that if I flip this over, it becomes cosine. So I could really just do this, reciprocate both sides. So the cosine would become the left side, and the right side would actually become root 2 over 2. I say, well, what can I take the cosine of to get root 2 over 2? That's what this inverse thing is asking here. I say, well, it must have been some sort of 45-degree reference angle because I only get root 2 over 2 for cosine in a 45-degree reference angle sense, or a pi force reference angle sense. So we say all students take calculus. We got a positive value for our cosine, so that must mean that we were either here or here. So these two angles are 45 degrees, x equals 45 degrees, or pi force radians. Or we say I must have been down here, which is 45 degrees shy of 360, which is 315 degrees, or 7 of these pi force or 45-degree angles. Okay, so that's how you solve trig functions more in general.